satisfying condition. It has a canonical vector field. So the way it works is that the condition tells me that d lambda has a one-dimensional kernel. So I take something generating the one-dimensional kernel, and I can normalize it to have lambda length 1. And the dynamics of this Ray vector field are of considerable interest. I'll actually give an example a little bit later in the talk, but of course we have many specialists here who just believe this, but a few who are maybe not specialists, and so arise naturally in Hamiltonian mechanics and studies of geodesic flows. And a particularly beautiful dynamical quantity are the periodic orbits, which are called Ray orbits. So for me, a Ray orbit will always be a periodic orbit of this canonical vector field on a manifold with a contact form. Another quantity, very beautiful, is the kernel of this one form, the so-called contact structure. That will actually be playing a very minor role in the talk, but does play a little role. Okay, that's our basic setup. Any questions about that? Okay. And then there's this conjecture. I've stated it exactly as it's stated in the paper. It's a kind of long-standing conjecture of Hofer, Weizsäcker, and Zender that says that if I have a tight ray flow on the free sphere, then it has precisely two or infinitely many geometrically distinct periodic orbits. So let me give a little bit of context. So HWZ themselves prove this if the contact form is non-degenerate. Okay, so that's going to be, I italicized it because that's going to be sort of the main point of the talk, is not having it. But remember, maybe in the morning, Mohammed said at the very beginning of his talk, say we have a Morse function, meaning the critical points are non-degenerate. So this is pretty much the analogous condition, but for a function on the loop space that arises from the contact form. So they assume that the contact form is non-degenerate, and they assume another condition, the so-called Kupka-Smale condition, which won't play a role in the talk, so I don't really want to talk about it. And they point out in the paper that these conditions hold generically. So roughly speaking, you can imagine they proved it in the generic case, and so the challenge is to prove it without any genericity whatsoever. Right. So yeah, so there you go. By the way, tight, I didn't quite say what that was. Remember, I talked about this contact structure. If I have a contact form, it has this associated contact structure, and so I'm demanding that the contact structure is tight. I won't say what that is, but on the three sphere, that just means that it's the standard one. So if you just look at the boundary of a ball, you can restrict the kind of standard primitive of the symplectic form on R4, and that will, its kernel will give you a contact structure that I call the standard contact structure. And tight in this case just means that it's giving the standard contact structure. So there's their conjecture. And yeah, so actually I've been interested in this conjecture ever since I was a PhD student. I think Mohammed was also talking about his days as a PhD student. So there's at least two reasons why I've always found this interesting. The first one is, like, why would I even think that the generic case is representative? HWZ, as I say, kind of prove this in the generic case, but you would actually think that perhaps if there is some kind of strange behavior, then it should exactly happen in the non-generic case. So for example, say I just look at functions on the two torus. There's two different questions I could ask. I could say, what's the minimum number of critical points that a Morse function could have? And that's easily seen to be at least 4. But actually, just a general smooth function on the two torus could have 3 critical points. So you certainly might think that there's some kind of pathological behavior hiding away from the non-degenerate case, and HWZ are asserting that it's not. So it seems that they're saying something like this kind of functional on the loop space has to behave rather differently than you would expect from Morse theory. Like on a finite dimensional manifold, you actually wouldn't expect that the kind of minimum number of critical points is realized in the non-degenerate case. So that was always interesting to me. Another question is just how do we even study this question? So it's come up several times already in the workshop. Normally, one just assumes that something is non-degenerate, and then you have something like Morse theory. You have a lot of tools in that case. So, there's kind of contact homology, things like that. But yeah, we can't use those, at least on the face of it, because we don't want to assume that the contact form is non-degenerate. So we have to do something. So in the finite dimensional case, there's so-called like Lustig-McShnellaman theory, and you sort of want to try something like that, but it's got to be pretty good if you're going to see this kind of tour infinity kind of business. So yeah, so sort of my main interests. Are there any questions about that? So maybe I should just say I won't write on the board, but first of all, there are examples with two orbits. Obviously HWZ were aware of this. That's why they stated the conjecture, but it's good to see the example. So in general, if you want to find rate flows, a very classical way to do it is to take a Hamiltonian, say on R4, that doesn't depend on time, so-called autonomous Hamiltonian, and then its dynamics have to occur along the level set of the Hamiltonian. So for example, if the Hamiltonian, if the level set bounds a star-shaped set and say is compact, then there's a natural contact form on it. So for example, if it's star-shaped with respect to the origin, you can exactly just take this standard primitive of the symplectic form on R4 and restrict it. You'll get a contact form, and the Rabe orbits will exactly agree with the periodic orbits of the Hamiltonian. So that's also just motivation for thinking about these questions for the non-specialists is, autonomous Hamiltonian flows are of kind of central importance in the dynamics of classical mechanics, and they often give you examples of Rabe flows. So anyway, so then you just have to find some classical mechanical system with only two orbits. So you can take the Hamiltonian giving the boundary of an irrational ellipsoid, which is going to correspond to a well-known physical system. So that gives you an example with two, at least when the ellipsoid is irrational. Okay, so there's a related conjecture. I have a paper here. It might be hard for many of you, but probably not all of you to parse because it's in Russian. So what is this? This is the 1974 ICM address of Anosov called geodesics in Finsler geometry, and I translated a little bit of it. Personally, I also don't speak Russian, but I had both Google Translate and a friend who speaks Russian. So anyways, I think it's interesting because it's always interesting to know, like, the people who popularized these questions, why were they even thinking about them in the first place? So I think actually Ko brought up Finsler metrics briefly in his talk when he talked about sometimes you want to go away from a Riemannian metric to a Finsler metric to have a nicer situation. So why was Anosov interested in Finsler geometry? He said, one reason is to understand problems of Riemannian geometry that are associated with their variational nature alone and don't really have to do with coming from a Riemannian metric. Okay, so anyway, so maybe better to make it concrete. So he says, let's look at closed geodesics on the sphere. So for example, in the surface case, which is relevant to what we're doing, for all, say, compact surfaces, in the Riemannian case, you have infinitely many geodesics, closed geodesics. And so if that's coming for some kind of purely variational reason, you would expect that that's also true in the Finsler case. So a Finsler metric is like a generalization of a Riemannian metric where you just sort of specify like a non-symmetric norm in each tangent space, whereas the Riemannian case would be when it comes from an inner product. So again, it's not so relevant to the talk, so I don't want to write out the definition. More is the philosophy. So anyway, so in the Riemannian case for surfaces, you always get infinitely many geodesics, but what Anosov points out is in the invertible Finsler case, in the irreversible Finsler case, there's a famous example of Katok that contrasts that, where you just have two closed geodesics. So something different from the Riemannian case. And he makes the following question. So he says, although the number of closed geodesics that can be expected on the basis of calculus of variations is usually very small, maybe it's unimprovable. So eventually this led to the following question, which was kind of much studied in the Finsler context. These are all three different sets of authors who asked about it. I said in the S2 case, I know that I can have two, again, in the Riemannian case, you always have infinitely many. In the S2 case, is it true that you have this two or infinity phenomenon? So that was interesting for them for a long time too. By the way, so just some more context. In higher genus on the surfaces, you have infinitely many in both the Finsler and Riemannian case. The issue is that sort of the arguments, even in the Riemannian case, when you have some genus, are a lot simpler than in the S2 case, and don't work for the irreversible Finsler metric.
The result of cathode, you said it was on S2 or
on S2 in the irreversible Finsler case, like the one that I think Ko was talking about, the irreversible Finsler.
Examples would always be like this.
Yeah, but I'm just talking about the surface. Everything in this talk stops above dimension 4, and so for anyways, just surfaces for mine. But that is a direct quote from Anasath. He was also talking about the surface. Oh. Any more questions while I'm stopped or anything? Okay, so here's the theorem. So say I have a contact form on a closed connected 3 manifold, and the Chern class of its contact structure is torsion, then there are always either 2 or infinitely many simple ray orbits. So it's a recent theorem. It's from last year, about a year old at this point. Let me just point out some corollaries. Okay, first of all, this does imply Hofer-Wysocki-Zender's conjecture. The reason is simple. All I have to do to check whether this theorem applies is that the Chern class of the contact structure is torsion. But their conjecture was just about the 3 sphere, for which this characteristic class is actually 0. So it obviously applies. It also implies the 2 or infinity conjecture. That's a little more interesting, but also pretty standard. I mean, there is a contact form on the unit tangent bundle whose ray flow projects to GD6, and you could just check that that's torsion. Let me just say, I won't write on the board, but there are many results which are related to this. In order to keep the talk focused, I didn't state them, but there's, well, personally, I proved a result with Hutchings and Dan Parmilano doing the non-degenerate case of this. In the non-degenerate case, there's also more general work of Coulon, Denois, and Rechtman. There's a lot of other work too. I mean, maybe the starting point is the work of Taubes, showing that there's always at least one orbit, which is generally called the proof of the 3-dimensional Weinstein conjecture. We don't want to go into all of that. But I do want to say something about what do we know about the case with 2 orbits, because that's actually pretty cool, in my opinion. So I'm saying you always have 2 or infinitely many, so it's natural to ask what happens when you have 2. Well, first of all, you always have at least 2. That's something I proved with Michael Hutchings about a decade ago. And actually, even in the case of the sphere, that was not known at the time. So that's sort of the first part of this 2 or infinity conjecture. But anyways, there's actually a lot that is known when there are exactly 2. So what you learn is that the manifold is actually a lens space. And the contact structure is not only tight, it's just universally tight. It's even universally tight. So to put this in some context, remember HWZ, we're asking about the tight contact structure on the 3 sphere. So that one does indeed have 2 or infinitely many orbits, but there are all these other contact structures, the over-twisted ones. And so this theorem combined with our other theorem says that every contact form on all the over-twisted contact structures on the 3 sphere have infinitely many ray orbits. So that this finite business really only applies to the tight case.
And all the lens spaces actually have a.
Yeah. As long as you don't include S1 cross S2 as a lens space. So you can just take a quotient of the standard contact form on the irrational ellipsoid. They do actually have that. Yeah, and almost surely these are these are the only examples. There's other interesting relations that I don't want to go into, but they're pretty cool. So maybe I'll say one. So for example, if you have the 3 sphere and you have exactly 2 orbits and their periods are T1 and T2, then the product of their periods is actually the volume the 3-sphere. So pretty cool. Okay. So any questions or anything like that? Yeah.
How often is it, I don't know much about it, how often is it that the first term class the contact form is torsion?
Right, that's a great question. Well, you know, whenever the manifold is, say, a rational homology sphere, that's it's obviously true. So that's in some sense maybe most 3 manifolds. But you know, for geodesic flows, Finsler flows, etc., the corresponding contact structure is always torsion. I said so just in the case of S2, but it's also true for the other one. So you can actually reprove these kind of theorems about Riemannian geometry this way if you want. You know, anytime you admit an Anosov flow, then the contact structure is torsion. So it covers a huge number of cases, including the HWZ cases, but not all cases. However, importantly, it almost surely covers every single case with finitely many orbits. And I'll maybe return to that on the very last slide if there's time. So probably if it's not torsion, you have infinitely many orbits, I'm sure. Yeah.
Is it known that generically, if it's non-torsion, you have infinitely many orbits?
Yes. If it's not torsion, then generically you have it. Okay, more questions? Okay, so in the remaining time, I want to just try to give you a sense for the proof. And okay, so so basically, let me say even before I start to get into the argument too much, is right. So to put this in some context, we need something that's going to work even in the degenerate case. And so we don't exactly, at least here, want to write down some kind of floor theory. Rather, we end up getting a kind of geometric structure that will eventually come out of floor theory, but it will arise in a rather indirect way. So here's going to be our plan. So under the assumptions of the theorem, so in other words, that the Chern class is torsion, and if I assume that there are finitely many simple Rabe orbits, I'm going to find what's called a global surface of section for the flow. So let me just draw you a picture. So here is a picture of an annular global surface of section for the flow. Let me just say a little bit more just to walk you through it. So I'm looking for an annulus in my 3 manifold. The interior of the annulus is going to be embedded. The thing is going to be immersed. And the key point is that every single flow line is going to be is going to hit the annulus both forwards and backwards in time. So this is living in the 3 manifold, and you should be thinking of the Rabe vector field as transverse to it everywhere except at the boundary, and the boundary are actually going to be Rabe orbits. So if I have such a thing, I can define what's called a Poincare return map, and that's what I'm illustrating with this picture. I start at a point X, and I flow until I hit the global surface of section again. That's my return map, P of X. And the point is that once I have a global surface of section, all the dynamics of the 3-dimensional thing are encoded in this 2-dimensional return map. So I'm doing a kind of dimensional reduction. Okay, any questions about that notion of a global surface of section? And you know, we're producing this under the assumption of finitely many simple orbits because we can assume that, otherwise the theorem would automatically be true.
S is inverse, but the interior is embedded. So
that's right.
So only the boundary can be like multiple colors.
That's right.
Oh, okay.
Right. Exactly. Yeah. So as I was saying, if you have such a global surface of section, you have this Poincare return map. I walked you through how it works. You can check that it actually preserves d lambda, which is an area form. So it's not just any map of an open annulus, it's an area preserving map of an open annulus. The periodic points are in bijection with the Rabe orbits, and there's a famous theorem of Frank's, you know, from the 90s or something, which says that if I have an area preserving homeomorphism of an open annulus, so kind of any, doesn't even have to be smooth, then if it has at least one periodic point, it has infinitely many. So So hopefully then you understand sort of point zero of the strategy. Namely, if I can find this annular global surface of section, I'm done. The reason is that the boundary of, so maybe I'll just draw it on the board, just because I don't want to go back to the previous slide. I have this annular global surface of section. The boundary already gives me 2 orbits. So if I have more than 2 orbits, then I have to have some interior orbit. And then Franks is telling me that then I actually have to have infinitely many. So I'm done. So the whole game is to produce this annular global surface of section. That's the strategy. So yeah.
Didn't you say that you're gonna find this on the assumption there's only finitely many simple orbits?
That's right. Right, because we want to prove that there's 2 or infinitely many orbits, and we already know that there's at least 2. So we can, if we happen to have one with infinitely many, then we're done. So we can assume that there's finitely many. Importantly, if there's not finitely many, then it is known that that this cannot exist. At least unconditionally, you cannot have an annular global surface of section. So you need something. And if there's time, I return to that in the. Does it make sense, the strategy? Okay. All right, so how are you actually going to find this global surface of section? Well, there's a beautiful idea with a long history, at least in the non-degenerate case, that we have to try to implement here. So we're going to try to find it. It's supposed to be an annulus. So instead of finding it directly, instead we're going to look at my 3-manifold cross R and use the theorem of the theory of J holomorphic curves. In particular, this thing is supposed to be an annulus. So I'm going to try to find a cylinder in R cross Y projecting to the global surface of section. And it turns out that the right cylinder you want has index 2. Let me try to say, give at least a heuristic why that's true. So the basic idea is that to first approximation, what this allows me to do is it allows me to think of this problem of finding a global surface of section for the flow, which is a pretty hard problem. Instead, turn it into a problem of trying to foliate this 4-manifold X by copies of this cylinder. So what I'm supposed to imagine is I take my cylinder, it's real dimension 2. Index 2 means it lies in a 2-dimensional family. And the hope is that as I move in the moduli space component containing C, okay, so that's a 2-dimensional family of 2-dimensional curves. Maybe I can show that that exactly foliates this 4-manifold, and maybe that implies that the thing has to project to a global surface of section. So that's sort of the geometric idea. I'll take questions about that because this is a very important idea. I mean, it has a very long history. It goes back to HWZ themselves. But there are a lot of new aspects here. Perhaps like the main point being that here the contact form is degenerate, but a large part of the J holomorphic curve theory comes in the non-degenerate case. So I said, you have kind of different floor theories. Later, we're going to use embedded contact homology. That doesn't make sense in the degenerate case, but there's even more basic things. Like I just talked about the index, but in the degenerate case, this might not even be a Fredholm problem. So there's kind of a lot that you have to do, and you also have to get very lucky. So it took us like, I don't know, maybe a decade to do this, and it was a combination of needing a lot of luck and just having to do a lot of work. Yeah.
But the previous line, so this cylinder annulus is going to have 2 boundaries.
Right.
That presumably are also orbits.
That's right.
And then there's going to be an extra one inside.
If there's more than 2.
Yeah, so what happens when there's 2?
Right. Then you just have some, then the return map is just some map of this annulus. Like it could just be a twist of that annulus with no periodic points at all. So you could have 2, like in the case of the boundary of an ellipsoid.
Oh, I'm sorry. Okay, I understand. I misread this thing.
No, please ask lots of questions because, yeah, good to be able to follow what's going on. Are there more questions? Yeah.
Maybe this is something you're gonna go into, but like given a J holomorphic curve, how does one determine if it gives you a global surface of section?
Great question. I'm gonna go into that in a little bit. I'll defer that for a little bit, but that's a great question. Yeah. So I would say in the non-degenerate case, it was previously pretty well understood, and we had to understand how to do it in the degenerate case. And I'm gonna go into that. Are there further questions? Okay. So let me then break this down into two basic questions, both of which are substantial. And in a way, our paper is sort of 50% devoted to one and 50% devoted to the other. So there's really two aspects that we have to understand. The first is exactly the question that was asked. P1, that's what I'm calling P1. If you just give me a random J-holomorphic cylinder in this thing, how am I going to know whether or not it projects to a global surface of section? That's exactly P1. P2 is maybe I even find some nice criteria. How am I actually going to show that there is a J-holomorphic cylinder satisfying that criteria? Because after all, the J-holomorphic curve equation is some PDE. I mean, maybe I can solve it, maybe I can't. I have some conditions. I mean, how am I actually going to find one? So both are substantial. Okay, so let's talk about P1. All right, so there's a very important idea here, especially for people who are kind of, interested in this in more than just a casual level. So what ends up being key is the rate of convergence to the Rabe orbits at the end. So basically, maybe the most important point about P1 is that we really still want exponential convergence to the Rabe orbits at the end. So I've drawn a picture of some J-holomorphic cylinder. So you're supposed to imagine this as an R cross Y for some degenerate contact form. It's going from one Rabe orbit to another. When I write this kind of picture, I'm saying it's going to converge to gamma 1, but what I'm saying is I actually want it to converge exponentially fast to gamma 1 as I go far enough up in the symplectization, and similarly to gamma 2 as I go far enough down in the symplectization. And for some context, in the non-degenerate case, this is kind of just a standard thing that comes out of the theory that you get this exponential convergence. But in the degenerate case, we're going to impose this condition, but then it's going to be quite subtle how we even find cylinders with this exponential convergence in the first place. But the first point is that this makes sense without any kind of non-degeneracy, degeneracy, etc. We just want exponential convergence. There you go. If you liked the Morse theory example, you could still wonder, like, I have a flow line between critical points, but maybe the thing is not Morse anymore. How fast is that flow line actually converging to the?
But it's very shocking. In Morse theory, it's somehow critical points is sufficiently degenerate.
Right.
Expect to do anything satisfying this exponential.
Exactly. I'm glad you mentioned that because in my view, that's sort of the miracle about the whole thing. Yeah, exactly. Right. So it's nice enough to say we want this, but then that gets to P2. How do you know that there's anything satisfying that? And that's kind of the miracle of the whole thing. Yeah. I'm glad you asked about that. And it's some kind of miracle of embedded contact homology at the end of the day, that there's anything doing it. Right. Okay, so to elaborate on that a little bit, there was a question earlier about, in the non-degenerate case, what kind of criteria actually do guarantee that you get a global surface of section? So let me go through them a little bit. I mean, I sort of put 4 and 5 in parentheses because I just want to give a flavor of the thing. So here we're just talking about in the non-degenerate case. Obviously, I want to know what I can do in the degenerate case, so let's review what is known in the non-degenerate case. So the first condition is, so we have some cylinder, we want its index to be 2. That makes sense because remember, I wanted a 2-dimensional family of 2-dimensional things in order to sweep out this 4-dimensional manifold. Also, I want the cylinder to be embedded. Now, 3 is probably the main point. I look at the moduli space containing my cylinder, and the main point is that I want it to be compact. Probably the most important condition to understand about this kind of thing. The reason being that what you can imagine is I start with my cylinder, its index is 2, so locally I expect to have some 2-dimensional family of degeneration, so I move a bit, but eventually it could break. I think like maybe Mohammed drew a picture of flow lines breaking. Then that would mean that the thing is not compact. And if it breaks, this game of following it around ends. I'm not going to see all of R cross Y. So that's maybe the key point. Then there are some other points, like you wanted to have odd Conley-Zender index. There's this kind of number theoretic kind of thing that you need to check. Maybe I won't go into those too much, except to say that a lot of these have to do with what I guess you could call intersection theory. So, you know, as I move in my moduli space, even if my cylinder was originally embedded, I might get some other cylinder that's intersecting it. And I don't want that, because I really want it to foliate all of R cross Y. And there's a whole industry of what you could call relative intersection theory, and these kind of conditions come up. But it's all pretty well understood. Yeah, so what I'm saying is, you know, basically the first kind of criteria are going to tell you that the curves cover everything. The other two are going to tell you that the curves are disjoint. And you also have to worry a little bit about the return time near the boundary. I mean, it's an elaborate thing, but it's pretty well understood. You might also wonder, like, how does sweeping out all of R cross Y guarantee that I'm actually going to get a global surface of section? The point is, any one of the curves in this moduli space are going to give a global surface of section. And if you like the theory of open books, maybe a good way to think about it is the moduli space is two-dimensional, but it has an R action. So when I quotient out by that R action and get this compact moduli space, it's going to be a one manifold, so it has to be a circle. So I'm just going to have a circle parameter. I'm going to have an S1 family of cylinders, and it's going to give me something like an open book as long as I see the whole manifold. And it's always going to be transverse to the Ray vector field if you sort of unwind it. That's kind of the picture. Anyways, I'll stop in a minute to see if you have any questions, but let me try to get through P1. Okay, so that was what happens in the non-degenerate case. Now let's say we have exponential convergence. What do you do? Well, actually, in a way, it's not so hard. Basically, there's a theory. Again, we saw some Sobolev spaces a little earlier. In the degenerate case, they don't quite make sense, but you can use what are called exponentially weighted Sobolev spaces. That's actually a kind of well-known theory. And so you get a corresponding weighted Fredholm index. So for example, originally you wanted the index to be 2, but now you want the index of this weighted Fredholm problem to be 2, all that kind of stuff. There's an automatic transversality, etc. So there is some kind of complicated stuff here, and also just work to be done, I guess, because not all of this had been done before. But in a way, once you have the exponential convergence, it's not so bad. It's really sort of what Mohammed was saying, like probably the hardest part is how do you actually know that there even is a cylinder like that in the first place? Okay, so are there any questions? Because this is all I really want to say about P1. So P1, remember, was just what are criteria for getting a global surface of section?
So you're saying that if you replace by this exponential weighted small Sobolev space, then the previous operator, like the operator that computes the index would be Fredholm.
Yeah.
That's a special code or something.
Right. I mean, there's some operator, and in the degenerate case, you can have 0 as an eigenvalue. But if you have an exponential convergence, you can move the eigenvalue by delta a little bit, and it'll go to being like delta, and then everything will sort of work.
Okay.
Yeah. I mean, it requires some work for sure, but basically everything works pretty nicely if you have exponential convergence and you just use exponentially weighted Sobolev spaces.
So I don't know, maybe I'm getting ahead. All this is sort of, you seem to be suggesting that you're gonna, you have a degenerate orbit, you're gonna sort of, get into a cluster of non-degenerate ones, right? And then make the cluster smaller.
More or less, yeah, that's right. Although that's actually very horrible. And that was sort of my original approach, which works terribly. So for example, it is not even known. So you take a degenerate orbit, maybe you perturb it a bit and it splits into 50 orbits. Then you would think, okay, if I perturb it less, it should definitely not split into like 100 orbits. But even that is not known and appears to be kind of a long-standing, it's like a 70-year-old problem, whether you can, even if you have like a critical point of a function and you want to approximate it with Morse functions so that locally there's only a bounded number of critical points arising from it, This is itself not known. So actually, things can get very horrible if you start with the degenerate orbit and start perturbing a little bit to get non-degenerate orbits. But yeah, maybe we should move ahead to P2. Okay, so let's give at least a sense of this. And yeah, so maybe the first bullet point is a version of what Ko was saying that works a little bit better for the problem. So instead of approximating the orbit by the non-degenerate orbits and seeing what happens to the orbit, it works a bit better to approximate the contact form by non-degenerate contact forms. You know, just like the Morse condition is generic, non-degeneracy is generic. Okay. So then you could attempt to find J holomorphic cylinders. Actually, your J, you know, it has some conditions compatible with the contact form. So your J is itself going to change, but that's not really a big deal. So now you have non-degenerate ones. You could, in addition, hope to find JN holomorphic cylinders somehow. We use the theorem of embedded contact homology. And then you could try to find this cylinder by taking a limit. So remember, I said eventually we have this cylinder, we need it to converge exponentially fast to the ends. And so this is the scheme. And this actually works. But to put this in context with Mohammed's question, here is exactly the kind of challenge. So each one of these is going to be converging exponentially fast just by the basic theory, but the rate of its convergence could be going to 0. And I need some kind of ECH miracle that it's not going to 0. Another big challenge, if you know something about embedded contact homology, is it does not count cylinders. The fact that these are cylinders is somehow important in the proof too. So you also need some kind of, it's not obvious that ECH is going to give you these cylinders either. Those are probably the main challenges. So any questions, Ko? I mean, maybe this is also related to your question. So yeah, so lots of nasty things can happen if you perturb a single orbit. Of course, this is not much better. Basically, the thing that ends up being important to keep track of when you perturb is not so much the orbits themselves as their action. So when you perturb, you actually can get a lot of bad things, but at least everything is going to have fairly controlled action. So roughly, if I have a degenerate critical point, a degenerate orbit, I perturb it, maybe I could get 1,000 orbits arising near it, but they're all going to have roughly the same action as the degenerate one.
But then you're saying like for each end, you're guaranteed to have some good orbit that is sort of bound and another one is sort of, you have some sort of cluster, right?
That's right.
You find a good one that's sort of.
That's right. Exactly.
And here we don't have like a splitting of the syncretization.
A splitting of the symplectization?
Because you choose the family of the complex structures that might give you like kind of like a SFT type splitting.
Right. No, yeah, I mean, at every n, I want to just pick my Jn to be compatible with lambda n. So the Jn's are going to change. For every n, I have a contact form lambda n. It's going to have a different Rave vector field, but I always want Jn to take the R direction to the Rave vector field and rotate the contact structure, you know, positively with respect to lambda n. So for each n, I'm going to get a splitting, and then the splitting will differ a little bit, but it all is going to converge even in C infinity to a nice thing on a manifold. Are there further questions? Okay, so there was this crucial point, but I already sort of said it. You really need to understand, how does the decay rate not go to 0? Okay, right. So how do we actually find these cylinders? This is where we use this floor theory, in particular embedded contact homology. So I'm just going to give a very quick crash course. You might as well just set y equal to the 3 sphere, because that's anyways the case of HWZ's actual conjecture. So, right. So it's a chain, it's the homology of a chain complex. It's going to be a floor type theory, so I can go through it particularly fast since we've seen a lot of that. Maybe comment on some differences. Rather than being generated by a single orbit, it's generated by sets of orbits. And rather than the differential counting something like cylinders, it just counts these mysterious ECH index 1 curves. The point being that the curves are mostly embedded. So I think I have a picture on the next slide of how you should think about it. But maybe I'll also just draw one. So, you know, in general, what you should be imagining is that the holomorphic curves, you know, they could have genus, etc., but they are going to be mostly embedded. And very importantly, it's isomorphic to the Seiberg-Witten floor theory. So it allows us to translate knowledge about the low dimensional topology of Y into knowledge about its contact and symplectic geometry, which is going to be important because we want to produce a lot of J-holomorphic curves. Okay. So, so keep that in mind when I talk about this. Again, we want to produce a lot of J-holomorphic curves. Index 2, so far I talked about the differential curves. The index 2 curves are going to be the ones that actually are useful, right? We want index 2 curves for this global surface of section. And the point is they define another map on ECH called the U map. And the first very nice fact coming from the isomorphism with Seiberg-Witten is that this U map is actually non-trivial. In fact, it's strongly non-trivial in that any power of the U map is always going to be non-trivial. That's also not an obvious thing. Like there could be no index 2 curves at all in principle, but actually it's not true. It's like saying that symplectizations are always uniruled, which is pretty surprising in dimension 3 that this is always true.
This uses like C1 versus.
No, that's going to be true in general. Oh, I mean, yeah, this is going to be true in general. There's only one point where we use C1 not 0. It's always going to be true that U to the n is sort of.
C1 is non-zero.
Yeah, if C1 is non-zero, then you might not be picking up like null homologous orbit sets and things like that.
Yeah.
Okay. So there's another fact about ECH, which is a little more in the weeds of ECH, but is somehow very important to this issue of how do you know the exponential convergence doesn't go to 0. And it's what's called the partition conditions. And maybe it's the first part of the theory that is probably not well understood by anyone other than the specialist. So it turns out that the ends of my curves are determined combinatorially by the local flow around the Rabe orbits in a very kind of intricate but combinatorial manner. So it's probably best to just illustrate this with a picture and with a chart. Unfortunately, the chart is a little bit hard to see, but I can at least try to point you through the chart a little bit. So here's how you should think of an ECH U-map curve. It actually could have multiple components. That's why this one has 2. But we're really interested in the non-trivial component. We have an orbit set alpha, an orbit set beta, and what the partition conditions tell me is the following. Let's imagine that those 2 red orbits for alpha are both just different covers of the same orbit. So maybe one is a 2-fold cover of an orbit and maybe the other is a 3-fold cover of that orbit. Let's call that orbit gamma. So I know that I have in total 5 covering multiplicity at gamma. And so what the partition conditions tell me is, say I also know the rotation number around gamma. That's just like saying the local rotation of the linearized flow around gamma. It's just a number between 0 and 1. Then I can do some combinatorics to tell me what the answer is. So I can literally look at this chart. This is saying if the rotation number, say, is 1/2 plus epsilon, and I'm in the 5 case, then I had to have had 3 ends, one of which is a double cover, one of which is a double cover, and one is a single cover. So that tells me, for example, that this particular thing could not happen because I only have 2 ends, right? So I could not have a 2-fold end and a 3-fold end at a thing of rotation number 1/2 plus epsilon. The reason that that's so important for us is because in our head, we should be imagining cylinders. So cylinders then are just saying that this number is the actual number. So it allows us to rule out many possible rotation numbers. So like with the example I just worked out, it's telling you the rotation number could not possibly be 1/2 plus epsilon. In the example that I gave you, it's telling you that that thing had to have been at a rotation number, maybe like 2/3 plus epsilon. So
the rows are rotation numbers,
yes,
and we of course cannot read anything, but what kind of numbers are there?
they're just, so what happens in the chart is it's been partitioned into, say, the bottom one is 0 to 1/8. The next one is 1/8 plus 1/7 to 1/7. The next one is 1/7 to 1/6. The appearance of 8 has to do with the top goes up to 8. So what you do is you give me the rotation number, which should be some number between 0 and 1, irrational, because we're in the non-degenerate case. And then this chart is only valid if the total ends of the curve have multiplicity no more than 8. So this chart just ends at 8. So you give me the rotation number, some ends less than or equal to 8, then I can just look in this chart and it will tell you what the ends had to have been. And we're actually interested in reversing this. Namely, we know you have cylinders by some other reason that I have not at all explained yet. And then that's going to tell us what the rotation number had to be. And the reason that that's very important is because the rotation number is itself related to the speed of exponential convergence. Yeah, so that's why we want to do that. Okay, so are there any questions about that? Yeah.
I'm guessing you can have other tables of different sizes, like instead of 8, like 12 or like.
Right, yeah, I actually wrote a computer program to compute this out to like 10,000 or something, or 1,000. Yeah, I mean, I never generated a table with it, but it's a purely combinatorial procedure involving enumeration of lattice paths. Yeah, okay. So, right, okay, so maybe I'll just say something a little more basic before I get into the weeds a little bit more. Okay, so yeah. So basically, remember that we want cylinder. And then the picture that I showed you is not a cylinder. And then I haven't really explained why we want cylinders, but take my word for it. Okay. And so that is supposed to motivate what's coming up next. So now we really want cylinders. We do have this UMAP on ECH. It's going to give us a bunch of stuff, but there's no guarantee that they're cylinders. And maybe the motivation for why you want cylinders is I really want to solve for the rotation number. And if I don't know anything about the curve, it's actually super difficult to solve for the rotation number. But if it's a cylinder, I can actually kind of invert this process and solve for the rotation.
Did you tell us you want cylinders or apply Frank's theorem from part 1?
Well, that is one reason that you want cylinders, but it's actually not the key reason, because if I had like a genus 12 global surface of section, you can't literally apply Frank's theorem, but there are related results due to like Le Calvez and things like that. The main reason we want cylinders is really because we want to solve for the rotation number, given that it had to have been a cylinder in order to deal with this exponential convergence issue. So that's actually a great question. Are there more questions? Okay, so what you can imagine is that maybe we're not going to be guaranteed cylinders, but we're going to get a lot of curves, because I said not only is u non-trivial, but u to the n is non-trivial for any n. And we really just want like at least one of these to be cylinders. So it's going to be some probabilistic argument. Similar arguments have occurred, but I think this one is sort of by far the hardest version of the probabilistic argument that has occurred. So in the end, we're going to conclude that actually with probability 1, the curve was a cylinder in this tower of n curves in a row. But anyways, and this is actually the only part where we use this torsion assumption. And the basic problem is, yeah, so how are you going to understand the topology of these ECH curves? And we actually define a new invariant for this called the score of the curve. I actually have a bonus slide at the end about the score, but I put it as a bonus because maybe it's not so important. Maybe more important, especially if you're a non-specialist, is that you also know that these curves are very, very small. They have very low d lambda integral. So if you want to think of them as flow lines in Morse theory or something, it's like saying that the values of the Morse function on the asymptotics are very close together. Okay, we know that. The reason we know that is as a consequence of this so-called ECH-Weil law says that the asymptotics of the curve grow like root n, but there's n of them. So on average, they're like O of 1 over root n. Okay, so then maybe I just wanted to try to understand this. So this is getting a little bit more into this exponential convergence business. Remember, the idea being that we want to solve for the rotation number. So the point is, we use this score, a bunch of other things about getting the ECH business to get cylinders. Now we look at the rate of convergence of those cylinders. And we want to calculate to show that that's bounded away from 0. So the way you do that is you just assume that the rotation number, let's say it's at the positive end and say that it's converging to 0. The rotation number, it's maybe helpful to remember that it's always normalized to be between 0 and 1. It's actually only defined mod 1. I'm always putting it between 0 and 1. So I guess what you should really imagine is that if the theta ends, going to Coe's question, the theta ends are like the ends of this cylinder, and they're converging to some degenerate orbit. That's what you should imagine. And you know that the degenerate orbit, say, has rotation number 0. That's the crux of the calculation. But there's two ways that the rotation number for theta n could be converging to 0. Maybe this is the key point. They could be converging to 0 from above, or it could be converging to 1, in which case mod 1 is converging to 0. That's the only two ways the mod 1 rotation number is converging to 0. And what we want is we really want to force it to be converging to 1 and not converging to 0. So the game is, you know, if you work through and the reason, this might be mysterious why that's important, but if you actually just work through the known asymptotic analysis, that ends up being the key point. You really want the rotation number to converge to 0 and not 1. So the game is basically, we know that this thing is very, very small. And we're assuming that at the end of the day, I have only finitely many orbits. So that means that I have to be at some very high covers of these finitely many orbits, at least more or less. Because you can imagine, say, the finitely many orbits have discrete action, and once I get smaller than that action, I have to have gotten covers of them. Right. So then I look at that partition condition chart, and I check that if I was really close to 0, then I would have to have just a couple ends there. Maybe I have to have multiple ends there. Maybe I'll point again to the chart, although it's a little bit hard to see. But the point is you can check that there's a bunch of like 1, 1, 1, 1, 1s here. So if I was really, really close to 0 and I had, say, an 8-fold cover, this is saying that I could not have a cylinder, because it's actually saying I had to have 8 ends, all of which have multiplicity 1. So if I know that I do have a cylinder, it's forcing me to be on the other side of the table where I have an 8. But that's the good case. That's where it's going in the right direction. Okay. So anyways, that got a little bit technical, but I think I'll pause here because all that remains is to just try to sum up how it all fits together and tell you some open questions. So, but are there any questions about this kind of part that got rather technical?
Oh, so the CNs are like really small,
They're really small.
and then, but then in the limit, it doesn't. They're still okay. So you have like a finite number of orbits to start, right?
Right.
The CNs will end up spanning different collections.
That's right. Yeah, that's something you have to check. The basic idea is that remember that the UMAP counts curves through a mark point. So they're small, but they do have to go through a mark point. So there's like different scales of smallness here.
I don't understand.
Right. So you might worry that the CMs are just sort of converging to 0. Right. That seems to be the kind of thing you're worried about. Like you could imagine, for example, that I have an orbit gamma, and then the theta n. There's a theta n plus and a theta n minus, and maybe those are both converging. But you have to check that that can't happen. And the basic reason that that can't happen is that the CNs do have to go through a mark point. So using that, you can show that they can't just go from an orbit to itself. So so what you should imagine is that you have finitely many orbits. So therefore you have finitely many different actions of the orbits. And using this mark point argument, you can show that at the end, you do have to go from one orbit to another that have different actions. And so therefore, it gets into like this work, it gets into the sort of difference between the Hofer energy and the action. So in order to make these small, we have to get n to be very large. So you can't actually make the CNs go all the way to 0 without making their positive asymptotics get very large. So you get so anyways, if you sort of put it all together, you realize that the kind of thing that you're worried about can't actually happen.
Do you really mean an integral of CN d lambda is as small as we like? That's
right. Yeah, I mean you can find a cylinder. You can find a cylinder with integral as small as you like.
That's what you're using. Because like if you're gonna span, it's gonna always have non-zero d lambda energy.
It's always going to have non-zero d lambda energy. Right, but you also have control over this parameter capital N. That's sort of what I'm saying, like, you know, you have u to the n, which is the number of ECH curves in a row. So if you give me, you say I want d lambda n to be less than 1 billion or something, then I can choose capital N such that eventually I have lots and lots of cylinders of action less than 1/1 billion. But they're going to be asymptotic to something of very, very high action. That's what I mean, their Hofer energy is going to be going to infinity. So when you do this in practice, you have to be a little bit careful about how small you want it. Like, you wouldn't actually want to run it to 0. What you want to do is you want to look at the minimum gap between the finitely many orbits and basically split that by 2. You don't want to split it by kind of, you know, k for every k, because then you won't have good SFT kind of convergence because your Hofer energy will be going to infinity. It's a little bit of a subtle thing. Okay, maybe just because there will be a question and answer anyways. So let me just try to put it all together, answer any other questions people have. So just to kind of put it all together, we take lambda, it has finitely many orbits. We approximate it by lambda n. We use the UMAP, these new score ECH topology ideas to get cylinders. They have low action. We show their exponential convergence is not tending to 0. Then you show that they satisfy the criteria to project to a global surface of section, and you get the desired curve as a limit. That's the basic idea. I said it a little bit differently here because I wanted to say something that's actually true. But anyways, that's the basic idea. Anyways, there's lots of points, like along the lines of Ko's question about checking how everything fits together. You know, you have to be quite careful with it, but yeah, that's basically how it goes. Okay, so maybe I'll just state some open questions. Now that it's done, here's some other questions that are interesting. And you know, then I'll stop. So now that you have infinitely many, maybe the next natural question to ask is how fast that they actually grow. So you can look at the number of actions, of simple Rabe orbits of action less than or equal to t and ask, you know, how does that grow as a function of t? So as far as I know, nothing is known about it. Like, you'd like to say that it grows at least as fast as the primes themselves, but I think the conjecture others have convinced me is that it has to grow at least quadratically. So if there's positive entropy, then it has to grow exponentially in t. But in the 0 entropy case, it's an interesting question, and I think the conjecture is that it has to grow at least quadratically. Another interesting question you could ask, do I always have a global surface of section? I mean, under the assumption of finitely many orbits, I got an annular global surface of section. I can't always get an annular global surface of section even on S3. There are counterexamples. But I could have one with, say, genus 11. And if I knew that, I could probably use the Le Calvez theory to imply, you know, this result. But this would be very interesting in a way, because it would tell you that all Rabe flows on S3 are just special cases of area preserving diffeomorphisms. It would give some kind of total reduction of the dimension of the area. Another different kind of question, apparently these questions are ancient, like go back to Poincaré or something. It's about the kinds of Rabe orbits that exist. So you could ask, is there always an elliptic orbit? I mean, I'm saying if there's more than 2, there's infinitely many, but maybe they're all hyperbolic orbits. To put that in some context, it's known that the flow cannot be hyperbolic on S3. S3 doesn't admit a so-called like Anosov flow. So the flow can't be hyperbolic, but maybe in principle, all the periodic orbits could be hyperbolic. I heard that actually, I guess Poincaré sort of said something along the lines of this can't happen, but never gave a compelling argument. And you could also ask, say I'm still just going to R4, but I'm not interested in contact type Hamiltonians. That would be like star-shaped. You know, what else can I say? Well, it's known that there are examples that don't have any orbits, but the recent work of Prasad that suggests that maybe almost every hypersurface in R4, say, has 2 or infinitely many orbits, something like that. So yeah, so oh, and then there was also this question about what if C1 is not torsion? So there the conjecture would be that there's infinitely many simple orbits. So yeah, so I think I'll stop there.
Are there examples of implementing simple regular numbers with quadratic growth rate?
Yeah, so that's what Umberto Hrenovich was telling me. As I understand it, no one has written it down, but the idea is that someone who's pretty good should be able to write it down. But it's a little bit like musical chairs finding someone to actually do this. So I myself would actually not know how to write it down, but Umberto told me something like near a triaxial ellipsoid, you should be able to find something with quadratic growth rate. And I think he gave it to his PhD student to write it down, but he said it's actually very hard and maybe his PhD student won't write it down. It is expected that there are examples. Also, I think maybe like Croak, or so, I don't want to malign anyone, but someone actually, I think, tried to write something down, but there's a feeling that there's a gap in it. But a long time ago, 30 years ago.
So when C1 is not a torsion, you can the proof is that you can still find a cylinder, or like do you use some different arguments saying that there should be implemented?
Well, we don't know how to do it when C1 is not torsion, but you're saying in the non-degenerate case, what do CDR do? Yeah, that's a very interesting thing. I mean, they also take the UMAP curves in ECH, but they don't even attempt to get a global surface of section. Instead, they just kind of project them all and they get a mess and they do something that's called Fried surgery. And what they extract is something like, I forget exactly what they call it, but it's something like what you could call a global system of surfaces of section. So yeah, maybe they call it a broken open book. They extract a broken open book. So basically, in a global surface of section, every flow line has to hit the surface both forwards and backwards in time. Now you start with a flow line, it flows, and then maybe it hits something else. And then it flows and it hits something else. And if you think about that, in the non-degenerate case, you can deduce infinitely many from some. So maybe one could do something similar in the degenerate case. I don't know, but it's not how we do it.
Yeah, maybe it's a naive question, which doesn't make any sense, but well, suppose you have a sequence of contact forms that say actual convergence to something that's not smooth. But say you can still write down like continuous rate flow in whatever sense. Is it still reasonable to expect that some behavior about the rate orbit still hold in this case, or?
Yeah, that's a very interesting question. I mean, I guess I should have clarified that for us, everything is always smooth, but I think you understood that. But yeah, you could try to push the regularity as low down and start to see when things get interesting. So, and I think that's very interesting. I mean, this all should work for something like C2 or something, and then probably things get a little interesting around C1, and then they get really interesting around C0. And you should also specify whether you mean the contact form or the flow, because say like because you're taking a derivative. So if the convergence is in C1 on the contact flow form, then the flows then the vector fields are kind of C0 close, and that has its own strangeness. Anyways, the actual ECH spectral invariants are C0 continuous in the contact. And so that's interesting. Yeah, there are kind of people who study like what you could call sort of continuous symplectic geometry, and they prove interesting things. I think for this particular question, I don't think they've studied this. Maybe I'm supposed to be an example of such a person who is in this community, but I haven't studied this. I haven't given a lot of thought, but I think it's an interesting question. Yeah, I mean, let's say, for example, Franks's theorem holds for homeomorphism. So even I, kind of somewhat of a not much of a participant in this community, was interested in, can you prove Franks's theorem with symplectic techniques for homeomorphisms? Many have proved it for diffeomorphisms, but it could be interesting to prove it for homeomorphisms. And I don't think anybody knows how to do that. If you wanted a concrete question.
Oh, so for question number 4, do you mean something like a stable Hamiltonian manifold, or?
No, I mean, the work of Prasad is just a kind of general. So think of it from the perspective of a Hamiltonian. So say I just have a Hamiltonian on R4, and I look at an energy level. smooths proper. So I looked at a compact energy level for a regular value. So the work of Prasad has to do with kind of statistically, what do I expect? So for example, Prasad proves that almost surely you have at least 2 orbits. So there are examples with no orbits, like due to, say, Ginzburg and Gorel or something like that in that case. But if you have a pile of level sets of a Hamiltonian, with measure 1, the critical value has at least 2 orbits by the work of Prasad. And it doesn't require, it doesn't, for the R4 case, the R4 case. It doesn't require stable Hamiltonian. Instead, it requires what Prasad calls framed Hamiltonian, which is a weaker notion. It's not actually due to Prasad. It's like in the work of Fish and Hofer. The argument of Prasad builds on the Fish-Hofer-Farrell curve theory, which is phrased in the setting of framed Hamiltonian, which is more general than stable Hamiltonian. But any level set of a Hamiltonian is always framed Hamiltonian.
And maybe just a naive question. So you know that the ECH of this quantum manifold is like isomorphic to the cyber 4.
That's right.
But how is like the thing that ECH actually does not depend on contact form, or
Yeah, that's right. The ECH as I've defined it does not depend on the contact form. It only depends on the 3 manifold with the definition that I gave here. I mean, there are considerations along the lines of what Ko is saying. Also, there are these things like the so-called spectral invariants, which are sensitive to the choice of contact form. But as I've defined it here, in other words, if you just take this chain complex generated by orbits, mod out by this differential, what you will get is an invariant of the 3 manifold. By the way, though, getting to your previous question, I mean, it is interesting to ask questions about this in the stable Hamiltonian case too. It's just not what I had in mind when I talked about the working Prasad.
Okay, let's thank him.
Thanks again for the invitation. And I think, oh, no, sorry. This is the last talk of the day, but not the last talk. Thanks again for the invitation.